Okay, let's look at this LC circuit. Here I have a 3 millihenry inductor with a 1 microfarad capacitor, and it says that the capacitor is fully charged by a 12-volt battery. All that's saying is that I have a charge on this capacitor that's equal to 1 microfarad times 12 volts. So that means that it has 12 microcoulombs of charge. All right, and no current initially flows in the circuit. So basically, I've charged this capacitor and I've just hooked it up to this inductor. And I want to know a number of different things. First, I just want you to discuss how the energy on the capacitor and the inductor changes with time. Well, first of all, remember that energies, I have the energy stored by the electric field, that's in the capacitor, that's equal to 1/2 CV squared, or 1/2 Q squared over C. And then the energy that's stored by the magnetic field, that's in the inductor, that's equal to 1/2 Li squared. And so we talked about in class how this is sort of like the potential and the kinetic energy of a mass on a spring, that when the spring is fully extended out here, that it has all kinetic and no potential, or excuse me, all potential and no kinetic, and when it's at its equilibrium position, it has all kinetic and no potential. So in a similar way, we get this oscillation between magnetic field energy and electric field energy. Energy stored in the magnetic field in the inductor, and then energy stored by the electric field in the capacitor. And both of those, the maximum value for each of those are given as these, 1/2 Q squared over C and 1/2 Li squared for the inductor. So initially, for this part A, at t equals 0, all of the energy is stored in the electric field. And I know that because the charge is at its maximum. I have this maximum value. So initially, UE is maximum, and UB equals 0. UB equals 0 initially because the current equals 0. And then as time goes on, those trade back and forth. So if I were to plot these, I'm going to plot UE in blue, and UE initially is at maximum, and it's going to decrease and then go like this. All right, and now if I plot the UB, it's going to initially be 0, and let's see how it'll go. It'll go like this. All right, so at any one time, I have a certain amount of energy. All right, that is this maximum value. So at this point, it's all in, what is this? This is UB. And at these other points, the energy is UE. So I'm interchanging this energy between electric field energy and magnetic field energy. Okay, what is the first instant that the current in the circuit is 0? So let's write out that function. So this is part B. The function for the current is I. Actually, I think I've been using a lowercase I here, so let me erase that. I. This is the current at any time, is equal to I max, that's the amplitude of the current, times sine omega t. All right, the current in the circuit will follow this sine function. And the instant that the current in the circuit is 0 occurs when omega t equals 0. Because sine of 0 is 0, so omega t is equal to 0. And we can see that here actually in this energy, in this plot that I've drawn up here. Initially my current is 0 because the current is going to follow UB. UB, the energy stored by the magnetic field, will be at its maximum when the current's at its maximum, and it'll be 0 when the current is 0. So UB will follow the current. All right, so whenever omega t is equal to 0, that's when the current is equal to 0. And we can find that time. Well, actually, that time is easy, right? Because the first instance is just occurs when t equals 0, right? And that's when the current equals 0. The next instant, when I is equal to 0, when the circuit is equal to, when the current is equal to 0, occurs when omega t is equal to what? 2 pi. Or no, not 2 pi, pi. All right, the next instant occurs when it's equal to 2 pi, 3 pi, 4 pi, and on and on. If I think about this circuit going around in phase space, I get it occurs here and here and here and here and back and forth. So whenever that omega t function equals some integer value of pi is when the current is equal to 0. All right, but the first instant is when t equals 0. Let's see, when is the current at its maximum value? Let me clean this up. I'm going to pause this for just a second. All right, so for part C, if I want to know when the current is at its maximum value, the current is at its maximum value when I look at this, when omega t equals pi over 2. Because the sine of pi over 2 is equal to positive 1, and so that is when I have my maximum current. So to answer this question, I first need to know what omega is. Omega for an LC circuit is equal to the square root of 1 over LC. And so this is going to be the square root of 1 over L, which is 3 millihenries, 3 times 10 to the minus 3, times C, which is 1 microfarad, that's 1 times 10 to the minus 6. And that angular frequency let's see, I get 18,257. I'll keep all those significant, even though they're not really significant. This is in radians per second. So that is my omega, and so the time when my current is first at its maximum value is when 18,257 times t equals to pi over 2. So I just solve this for t, so I get, I just divide both sides, I get pi over 2 times 18,257. All right, so that time is 0.8 times 10 to the minus 5 seconds. That is the first instant when I get my maximum current. So if I'm plotting out my current here, current versus time, that is the instant right here. This is at t equal 8 times 10 to the minus 5 seconds. That's part C. Part D, what is the angular frequency for the oscillating current? All right, I've already answered that. That's that 18,257 radians per second. And then what is the charge and what is the current in the circuit at these particular times? So if I want to know the charge, I think this was E. And remember, this this part right here is D. I had to find the angular frequency already. If I want to know what is the charge, well, the charge is equal to the maximum charge, which I've already found, that's that 12 microcoulombs times the cosine of omega t. Remember, the energies are going to switch back and forth. So when the inductor energy is its maximum, that means that the capacitor energy is at its minimum, or at 0 rather. So so the charge on the capacitor will be 0. So since the energy switch back and forth, that's why I have a sine function for the current and a cosine function for the charge. All right. So and also because it's a derivative. But all right. So here I want to know what is the charge at 2 seconds. So I just say Q is equal to 12 times 10 to the minus 6 times cosine of my omega, which is that 18,257 times 2 and I get 8.9 times 10 to the minus 6 coulombs. Let me make sure that I was in the right mode for that. Yeah, I'm in radian mode for that, so that is correct. 8.9 times 10 to the minus 6, or 8.9 microcoulombs. All right, and then for F, I want to know what is the current. So this is just I equals Im times sine omega t. And you do a similar thing here. I've already found my Im, I think, haven't I? I have not. So we'll need to do that first. I'm going to do that right here since we have these equations drawn out here. If I want to find my maximum current, I say that UE is equal to UB. I know that those two are equal. It's like saying the kinetic and the potential energies of a spring are equal. At their maximum, they're equal because they're conserved. And these are our field forces, just like in that case. So I have conservative forces that act. So this energy is never actually lost. So I have this electric field energy is equal to the magnetic field energy. And I just say 1/2 Q squared over C equals 1/2 Li squared. And then I solve for I. And this is going to be I max. Those halves cancel out. I get Q squared over LC, square root of that. I know Q, it's 12 microcoulombs, and I know L and C, of course. Let's see, I think I've already calculated this. It is going to be 0.22 amps. So that is my maximum current, which you need to find part F. And now that I find part F, I just plug that in. So it's going to be 0.22 amps times sine of that 18,257 times 2. I get 0.15 amps. So that's my current at 2 seconds, and I'm just using this function. All these functions you'll have on your equation sheet, so but you'll need to be able to apply them in the appropriate way, and also discuss how the energy is transferred back and forth between the inductor and the capacitor, back and forth, and it does that without any loss of energy because these are just field forces. Now, of course, that won't be true with the LRC circuit because now we'll have a resistor that will dissipate energy. And I think an LRC circuit, no, not quite. We'll come back to this in just a few minutes. I'm going to take a pause.